So first of all, I would like to thank the organizers, all the sponsors. It's really a pleasure to be here. And also, as I said yesterday, the conference is really a most interesting one because of the possibility to integrate Latin America. So the talk of today's session is on why we should consider computational intelligence. So the idea here would be really to explain a little bit what is semiotics and how we are trying to address this problem, and of course the motivations and some possibilities. So initially I would like to thank the sponsors, especially my universities and of course the local organization for this event. The agenda, I would like to start with some words and establish a quest for this talk. So then we move on to Persian semiotics. For those who do not know, I really much appreciate the insights that Pers posed. And of course, I am going to address the semiotic machine as we created. I am very glad that my co-authors are here and also provide a few examples of that. So as for the beginning of the talk, I would like to state that this is also a philosophical talk. I would like to open up a little bit the scope of the presentation out of science and go into the philosophy of computer science. Of course, that would not be the major part of it, but I would like to advise you that I am trying to address this point. The other one is that this is an ongoing research, which is obviously not complete, but at least I'll try to show you what are the current status and, of course, the possibilities. A little bit about us. I come from Recife, which is in the very tip of, if you trace a line, I am in the opposite corner of this continent, okay? So in the opposite, same latitude. So it's the closest point to Europe. So we have beautiful beaches, and sometimes it's hard to keep the students in the lab. And the very sad thing is that these beaches currently are really struggling with oil spills. I don't know if you have seen on the TV, which is really a shame. So, but our lab, it's called Computational Intelligence Research Lab. These are some figures. We are around for some time. And the major focus of our research is meta-heuristics, decision support, and now computational semiotics, but we do work on optimization and other topics. But let me start trying to pose this quest for the talk. And I would like to name it a new computer science. Because we have to understand what computer science can offer, and of course, what is missing, what it can offer, what it cannot offer, and what could be the avenues ahead. So, for example, I would say that computer science at the moment lacks a little bit learnability. So algorithms in general, if they are done without this worry in mind, so make them very boring. They do not create any kind of surprise for the user, but it could offer adaptation. The fact that we produce algorithms that are able to adapt to change in the environment produces a great number of possibilities for application. What it cannot currently offer, at least in an acceptable way, is explainability, even if we do computer science with AI. So in some way, what I'm trying to do here is to present computational semiotics as another layer, let's say, that together with computational intelligence can complement computer science so that we are able to present algorithms that are adaptable, but also that have this ability to explain the computation. And of course, this is what I said, computational semiotics could be one possibility for that. But let's talk a little bit about semiotics. Let me just ask very quickly here, who in this room knows a little bit about semiotics or have heard? Okay, that's great. Of course, this is a science, and this is not within computer science. It's transversal, it's a long-standing one, and of course, we are just using a very minute aspect of it. But as this is not necessarily a presentation for experts, I would like to start with a motivation. And I'll show you a picture that my niece sent to me. And then as soon as I received the picture, it was puzzling because when I look at that, it took me a little bit of time to understand the message. So let's do the same with you. What do you make about it? So, of course, you have three very cuddly things, let's put like that. So you can play with them, and also you could think of many other aspects. This is a toy. This is a toy. But this is not a toy. And our brain has the ability to classify this. It's not so quick, to be honest with you. It takes almost a second for that operation to come about. But it is interesting that we are able to understand the message without any label. And this is very powerful. My take is that we should pursue research to try to endow algorithms with these abilities. This is a demand from my niece. She said, if you are going to post this picture, you have to tell people where is the Instagram of Nico, which is her small pet. Good, but let's start with another motivation as well. How many Brazilians are here? 2. So you guys at least will know that in Brazil there are 2 chocolate boxes, the main ones. There is a red one, but let's stick to 2. And then if I ask you, Alfredo, which one you like? The blue one. And how about you, Dennis? The yellow one. So it's funny because the boxes are full of chocolate, as you can see, and sometimes people become very indecisive which one they could pick, because the chocolate boxes is comprised of many different chocolates. For example, I like very much coconut, so both of the boxes do have coconut one. I like crunchy chocolates, both of them have. But for example, this one, the same as Alfredo liked, has Swiss-like chocolate. The other one doesn't. So for me, the blue box wins. As for Dennis, raise your hand, Dennis. Okay, so let's assume that Dennis likes coconut also, but he likes a multi-layered kind of chocolate. And this has 2. Which the other one doesn't. So for Dennis, the yellow one wins. So what I would like to say here is that when you analyze things, you ask questions like which box, sometimes the best way to solve the question is to go inside, or, metaphorically speaking, to deconstruct the data representation and analyze this in another level. So when the presentation goes on, you probably will understand why this motivation is there. And then before talking about semiotics, let me tell you a little bit more about the inspiration and then motivation for me to do this kind of research. So when I was in my PhD in London, I studied with Professor Igor Alexander. He was supposed to be here, but unfortunately he had a health problem. And then let me tell you a little story that happened. It is a real story. He was a very active researcher and very busy delivering talks and stuff. And at one stage, he was invited to go to a school to talk to little kids, something like 8 to 10 years old. And the little kid, in the end of one of his presentations, asked him, "Professor, do computers can dream?" And then he was puzzled with that because he never thought of that, of course. That was in the beginning of, the end of the 80s, 1980s. And then he asked the girl what she was talking about. And then she said, "Can computers think of a blue banana with red dots?" And he was even more puzzled. Okay? And then he get back to the lab, and of course, as a very good professor, he delivered this task for us to work upon. Huh? And the thing is that the idea is very simple. It's basically what I've done with the chocolate box. What is a blue banana with red dots? Basically, it's a blue banana with red dots. But what is a blue banana? Well, a blue banana is a banana with color blue. And the same with red dots. Dots with the color red. So my point here is that neither of these concepts, the aggregate ones, are inside of our brains. However, we can construct things if we want. For example, let's do an experiment. How about a red banana with blue dots? Could you imagine one of those? Red banana with blue dots. So there is no such a thing in the real world. You have never seen, but very quickly your brain could make sense of that. And you can even have a little bit of sense if you like that one better or this one. And this is really interesting because we have this ability and we don't pay much attention to it, perhaps because it's too much, very much what we are as humans. So let's try to convey this or to transform this into computer science. So basically the idea is that in this case, we would like to convert or to deconstruct the elements from something that is abstract into more concrete things. Although bananas and blue things are not concrete in our brains, they are abstractions as well. But at least let's talk as if they are. The other source of interest for semiotics to me, as well as that story, was that in the 90s, I was very pleasured to meet an Oxford professor that she was talking about the brain and the pathways and all that. And it's interesting because in our brain, we can have many divisions, but for example, we can have a division between the back part of it and the frontal part of it. And of course, we can understand that there are two different pathways. When you are presented to an object, there are two different streams that go into your brain. One to decide what you are seeing, and the other where you are seeing. It's like two different parallel processes that will be combined to make sense of things. So that's another aspect that we thought about so that we could incorporate later in our models. The third source of inspiration was in the 90s when I get across the work of Ludwig Wittgenstein, which is somebody that actually make this link through language between the link between language and reality via logics. And this is very much known to us now. For example, let's say that we use Facebook. So in general, life is not as it is portrayed in Facebook. So somehow there is this dichotomy between what we say and reality. Okay, and then the fourth source of inspiration was this man. Although we don't use explicitly fuzzy logic, but the fact that Nov2019 were in the 2000s advocating that computations could be done through words, that caught my attention as well. Because basically, I'm not going through fuzzy logic, but the idea is that basically he substituted this Aristotelian concept of sets and belongingness to sets, like zeros or one. He translated that in a fuzzy membership function, meaning that instead of saying 38.7 as a limit between fever and no fever, or high fever and no fever, he had this idea to transform this boundary fuzzy, which is very sensible, because now, as humans, we do not need a thermometer. We just say high fever. This is different from fever. So how all those concepts could be put together and transformed into an algorithm? These are basically I would say, my motivations for that. So if you go to the dictionary, so computer science is basically mathematics applied to create code so that you can automatize tasks. But in this classical perspective of computer science, you have input, output, and the processing in between, so that the computer program maps inputs into outputs, like the mathematical function that maps x's and y's into y's. So this is a computer program. Of course, if we linked the output to the input, you can make this computation adaptive somehow. So basically, many algorithms, intelligent algorithms, the difference between the classical to the intelligent one is this connection from the output to the input. Why this is so important is because it's a very simple way for the program to be aware of what it's doing. So let's try to get back to example of the banana here. So if I type banana into this program, so it goes in the database, and there is a banana stored there, and then the computer retrieves that concept. Do you understand that? That's the classical flow. Whereas if I ask for a blue banana, the result would be none. But let's get back to one guy very important to us, to all of us. This is Aristotle. He was the one proposing deduction. Deduction is basically what I've just done with that previous example. Banana, fetch, and then I have the image of a banana. This is deduction. Basically, there is no surprise in the system. But how about if we go for non-classic perspectives of computer science? For example, inductive ones, like the ones suggested by David Hume, the Scottish. By the way, a Scottish man. David Hume. Huh? Obviously, he's not that famous, but we try to push his name forward. So the idea of David Hume is basically, as opposed to Aristotle, you can infer the model through data. So basically, you start from the end of the formal process and try to formalize the model, okay, but via inductive methods. So basically what Aristotle says is if you have the rules or the axioms of a system, you can write a program that can infer data. What Hume says is just the opposite. which is nice because we have lots of examples around. If we have examples, we are able to come up with models, in this case, computer programs. And this is basically the beginning of our quest here. So in summary, idealization, in my perspective, is up-down. Realization is bottom-up. I'm not taking sides here. I'm just saying that Aristotle and Hume, they are not in extreme isolated poles. They should be used together. This is my take-home message to you. So let's revisit that chart I presented before. What this means. So, if you have x's mapping into y's, and the use of a delta rule that can compute an error here, and this error being feedback here, so this system becomes intelligent. But if you invert, pay attention to that, you are inverting the function. So in this new proposition, the input is y, and the output is x. So not a big deal, but for our banana example, it made all the difference. Because now we can come up with a blue banana, which is not there. But if we make this induction, which is based on examples by Hume, plus deduction, so you can come up with blue banana. I don't know if you understand the step we added in the process so that we can solve a problem that before, by just using Aristotelian logic, we could not. So, about semiotics a little bit. So, if you go to the major dictionaries, semiotics, it's very, I would say, well defined. It's a study of signs, symbols, communication, or how this signification process happens. And of course, as a dictionary, they have fulfilled their duties. For us, that we are engineers, we have to materialize that. So the definition is there, but how can we construct, algorithms that are able to attribute meaning to things? And the rationale is already said, is this combination of induction and deduction. But let's carry on. There are two very important philosophers, actually, that should be named here now. So Fernand de Saussure is a Swiss linguist and semiotician, very famous, but very famous for the linguists. He created this dyadic perspective. What is dyadic? He said that things have two parts, signifier and signified. And this makes sense. For example, if I show you this, what is this? This is a glass. Okay, so according to Saussure, you have an object and a name for the object. Fair enough. However, this is not enough if we would like to solve more difficult problems. I mean, to communicate between humans, to communicate with machines, to find, for example, the meaning of or the likes of some objects. And then again, Aristotle come into play because at his time he created a concept that was further developed by this gentleman, Charles Sanders Peirce, which, by the way, is an extension of Saussure. So the idea here is that instead of having two parts, you have a triadic perspective. And this triadic perspective makes all the difference for us and for the quest we established in the beginning of this talk. Because without that, you are going to see in a minute, we cannot make sense that is different from me to you. So I'll give you an example. So for Saussure, the signifier are like that. So you have the concept of the tree and the name of the tree. Okay? So this is nice if you are analyzing a text, but without further interpretation. But what boring world would be that if we only have this kind of stuff? Because everybody would agree, basically. You would not have a different idea from me. So that's why I am insisting that the Aristotelian perspective of this rhetorical triangle is so important, because now you have a third part, which is the interpretant. So it's the figure of somebody that is observing the phenomenon. It's not only the name and the object, it's the name, the object, and the one looking at that, making sense of what is going on. But look, Aristotle created these 3 dots. Actually, he did not link the dots. The one who linked the dots was Peirce. So what is ethos, pathos, and logos? So in English, that would be credibility, that would be logic, and that would be emotion. So it's like the emotion would be somebody adding value to what is being said. So, or you could say speaker, message, and audience. Or, how about that? You see? So I don't know if the guys from Star Trek, they designed the main characters with this idea in mind. But it makes sense that Bones, Kirk, and Spock, they are prototypes of these classes. Okay, so but let's connect now with the difference between Peircean semiotics and Aristotelian one, / Peirce. So the idea now is that you have the triangle, the Aristotle triangle, with the edges connected, meaning that the semiosis, which is the attribution of sense, of meaning, it's a process that does not occur automatically. It takes time. Remember the first slide I showed you about the little dog? It took you a little bit of time for you to make the connection so that you understood that at that image there was a dog and 2 pets. So what I'm going to briefly show you are some details about semiotics that I find very relevant for you to understand our contribution. So there are 3 different steps. This is Peirce's triads. The idea is how you connect these arrows, these edges. So these are the contribution of Peirce regarding the connection. So you have 3 links. By the way, this link here is not solid because I'm trying to tell you that we are not to be afraid of computers because this is not solid. At the moment this is solid, within computers, we should be very afraid of them. Can you understand why? Because at that moment, when we have a solid link here, there will be no need for us. Do you understand that? Computers would be able to perform this connection between names and objects without us telling them via programming that this is the case. Well, but at the moment here is just for you to understand that these 3 parts. Let's move on and give you an example. So cat, but cat quotation is the name. So for that, it triggers an image in the interpretant brain. And this is very important because a cat for me probably is very different from a cat from you see? And this is what makes life so nice because we have different ideas, although the object is the same. If we see a cat and we name this is a cat, the person that is observing can have ideas. I like cats or I don't like cats. And the point I am trying to make here is that we should cater for that if we want to produce programs that have or ability to aggregate value. For example, in the previous talk, we were seeing lots of very nice robots, okay, little robots, but if the kid likes it or not, it's very difficult to forecast, because every kid's mind is different. But if we somehow are able to model that, we can either produce better robots or make better use of them, for example. This is just to tell you that if we are to make another reflection, at the moment we are very good at this. For example, we create in our programs variables, and we have attribution of values to them. When you code, you say cat equals that. This is what humans do. Of course, the name of the variable is something that the label we learn through experience. But this is really what scares me, because so far, professors like yourself that have been working on mathematics for a long time, you have been working on the right-hand side of the equation. The computers that are going to scare us are the ones that are able to create the left-hand side of the equation. And this, to my opinion, can be done using semiotics. So let's go to basic categories, which is the second part of Peirce. So what he did here was something very interesting. He came up with this idea of, by the way, let me explain that. Peirce was very concerned with meaning. So when he created every concept, he created a new word just to avoid old interpretation of the same word. So he created, for example, this word firstness, secondness, and thirdness. What did he mean with that? So the idea is that when I show you something that you have never seen before, the understanding, like the pet in the beginning, the understanding does not happen instantaneously. First, you take the basic impressions, and then from there, you move on to further reflections until you end up with the meaning, the final meaning of the concept. And the final contribution of Peirce, which is called the trichotomies, is basically when he further developed these ideas. I'll try to be brief here, but it's important for you to understand that. So this is the complete view. So you have, for example, can you see the Aristotle triangle here? Representam and interpretant, this is us, this is the object. So he superimposed on that the three different concepts. I mean, the triads, the categories, and now the trichotomies that I just mentioned to you. So all that together is a very sound attempt to create mechanisms to transform objects that are not existent into reality, like the blue banana. This is our thesis. We think that if we put all that together, computers would be able to synthesize concepts. So let's see how that boils down to some details here. So this business of representamen, which is the relation of the name with itself, okay, happens in three different steps, as Peirce mentioned. For example, when I say a word red, there is no possibility for me to explain red, because this is the very basic concept. I cannot go down. But I can say the redness of red. Do you understand that? So let me give you an example. Alvaro's shirt is red. Can you see? Could you raise your arm? This is red. Your one is sort of red. If I ask you, which one is more red? No doubt, if you have operating a completely okay visual system. But this is amazing, because I've never defined red to you. And this is what Persis is talking about. So there is the concept, which is this first impression, that then what it, something more than that, and later on what it represents to me. So another example would be cat, catness, and catness of a cat, of a particular cat. Do you understand that? It seems like crazy, but it makes sense. I'll try to make this reasonable in a moment. The other detail or aspect detailed by Peirce is when it relates to objects. So objects related to themselves. So for example, for example, who is this guy? Who is this guy? It's famous. Shakespeare, yes. So when I show a picture or a draw of Shakespeare, okay, you know that this is Shakespeare because the object represents the real thing. So when when I show a picture of Shakespeare, the time for you to decode is very small. But and this is an icon. When I show you an index, it requires you a little bit of time because, for example, you have, it's very faint here, but there are some steps on the sand. So here is an index because it's not an icon. I'm not talking about a person. I'm just talking about that somebody that walked there, like the footprints of Professor Bezdek. So from here to there, and now I think you can understand what Peirce said about firstness, secondness, and thirdness. So this is secondness of objects. And the third one, which takes more time, is when the object or the sign does not have any connection to the object it is representing. So for example, this symbol is a convention. We know it because we learn it. There is no link between this and what it means. There is a faint connection, but here is direct. And last one, which is the interpretant, firstness, secondness, and thirdness to the interpretant, meaning us. This is also very interesting. So because when we see things, the first impressions are the quality of what we are talking about. In Greek, this is called qualia. So the inner quality of things. And this is also very quick for the one that observes. Then comes a second step in this process of interpretation of the signs, which is the argument. Basically, this is the feeling. When I show you this, for example, you first have to understand by the shape and the color, etc. Oh, this is a pointer. After that, you come up with this idea, I like that. You know, the feeling or the effect. And finally, you realize that this has a purpose. But all those operations, they happen in a sequence, not so fast, almost 1 second, but they are important for us to make sense of things and create our opinions and stuff. So basically, what I would like to talk about Peirce is this, plus chaining, which is something really important for our contribution. So how are we with time? Who is 35, huh? Okay, that's fine. So chaining is basically when you put several Aristotle triangles, one linking to the other. It's like a conversation. When you start a conversation with somebody, you start with one subject, there is this conclusion that triggers another subject, and this goes on and on. That's called chaining. For example, this is what I'm suggesting for my or our student here to do after his PhD, I mean, to work on that, with an objective to try to create explainable algorithms. Because what we want, basically, is to create this sequence that can link from very basic concepts to more abstract ones and vice versa. So, for example, if I start with something here, I'm referring to this object, but basically what carries on is the concept of that object triggered by this to the other level. And this goes on and on. So, for example, when we talk here about one thing, in the end of this chain, this is what we are talking about. Do you understand that? So, it's a series of semiotic semiosis linking one to the other. This does not exist yet. But when this exists, we will be able to have computers creating lots of surprises to us. This is the background I would like to tell you. Let's talk a little bit about semiotic machines. This is the work we created, and then the objective is to materialize that. This work is a result of a joint research with Gottfried Vossen and Dennis, sit over there. And I'm very happy that we made it. And Dennis is about to finish his PhD in a few months. But let's start with another example. So this is Gottfried, and this is me. So we have a very strange habit of sticking our names in license plates. This is Gottfried Vossen, this is Fernando Buarque de Lima Neto. So we have this, and we also like American cars. So Gottfried has I think you are the only German person who has a Mustang. And I like also big American cars. So this is one match between us. So, but why this is here? Because when I talk about cars, Gottfried has a different interpretation of cars. Think of the chocolate box. So when I say that I'm talking about this car, he is thinking about this one. Of course, he's older than me, he has more money than me, okay? But my point here is that there is a cognitive gap, and I think we can create mechanisms that are able to match this, to understand this, distance between concepts. And the idea would be for us to have a process that would be able to decode the most relevant aspects when I mention car, and that automatically could map to his concept of cars. And this we created in the form of a semiotic machine, which is a change in, for example, a funnel, because I will use a metaphor here like queries in databases. When you type, I would like a car, so the query will, you have to add terms to it to reduce the number of options until you are satisfied. But this is not adaptive. It does not have this ability I was describing before. So the general idea is to add lots of funnels, but in between the funnels, you have the ability to expand again, because otherwise you are going to be narrowing down your scope. So the idea is to narrow down, then to allow it to open up again, like we do. Deduction, induction. Do you understand that? The link with the previous slide. So the two together, in my opinion, is key for solving this semiotic problem. So what is a semiotic machine? Semiotic machines are modular constructs that mimic semiotic chains, although we have not done yet, and jointly perform sign deconstruction using Persian triads, categories, and trichotomies, as I explained to you, by means of computational artificial intelligence techniques. If you are curious about that, the first paper on that is this one. So, Data, Knowledge, and Engineering. It was out last year, September. So you can have a read and take more details there. So, but basically the construct is very simple in itself. So the idea is that we have this funnel, then we allow it to open up again. So basically, we have some techniques that have this ability I mentioned before to extrapolate things. For example, I'm not connecting to particular technologies here. Just think of the concept. So we could have a technology that is able to create a Pareto front, and from those points in the Pareto front, we could project them in a map for the decision to be made. So that here, I must tell you, it's a turning point in this talk, because we are moving from philosophy to science now. So what we are talking about is how to materialize those concepts. And the idea here is to use, I think we have another slide that could explain the SADA model. So the idea of the SADA model, that could be, for example, there's no need for you to use just one model. You can have several ones. For example, if you are going to buy a car, the first one would be mapping your wishes to the seller. The other one could be mapping the seller to the banks that are going to fund the car. And the ones, of course, the last one would be the banks and, of course, the sale. But this is just an example of how the modules could be linked. It's up to you. Let me go back to the explanation of the SADA. So, given the time, I will just show you the next one. So basically, this is the SADA in a horizontal way. So for example, we could use self-organizing maps, artificial immune systems, and many other algorithms that are able to perform classification and clusterization, okay? And also, we could use later on genetic programming, fish school search, and other technologies that are able to perform the creation of that Pareto front. So the idea here is that you are going to use technologies that are able to do or to perform induction and deduction together, so you can come out of that limitation of Aristotelian programs. I know that it may seem complicated, it is not, and I'll give you an example for that. So back to the car example here. So let's say that now comes Dennis, okay? Also, the match is big cars, but Dennis likes red cars. So this is what we are trying to make. So we have to accommodate the concepts or the features that are relevant to me, to the features that are relevant to Gottfried, and perhaps to a new comer. And this, again, can be done, this is what we have already proved, automatically. In a car purchasing example, Dennis, I stole these pictures from your thesis. Not this one, but the coming one. For example, if I would like, this is the explanation of the SADA module. So if I would like to buy something, initially I have to narrow down like the funnel. So that's the first part of the SADA. which is search. Then, when I have this performed, I need to evaluate and also to discriminate, to separate things that I have collected. But if we stop here, that would be a regular query. I think the big jump was when we adjust again the scope of the query using these technologies I mentioned to you. So, for example, if we follow that stream I showed you, initially you have lots of options. They are put together in a Pareto front, and then after that, when we get the aspects that could be collected from internet, from previous purchase, or etc. So this could be useful for the adjustment in the scope of the selection. And then we come up with an answer. So have a look at this example. If somebody comes up with this query, I want a particular car, okay, and the car has some features. Obviously, we could create a map with all these cars classified or clusterized by their features. And then just for you to understand, if we are going to show this region of the map, that would equate to this. Do you understand? So the cars are organized according to their features. So basically what the semiotic machine does is to create a boundary between what are the cars and the regions in that map that are closer to the wishes of the buyer, and try to create another region of negative examples. So basically, this is a classification problem, okay? And in this case, we use genetic programming for that. Basically, this is what is going on. So we are trying to find what are the right components in a query that selects what I want and leaves out what I don't want. And the tricky part is because this has to mimic what a human is going to do. Therefore, it has to be adaptive, as I mentioned before, and also it has to accommodate the wishes from the customer in this case. Luckily, genetic programming can do that. So in the end, for example, that was the selected car for that particular query. And very interestingly, our approach can refine the initial scope provided by the buyer. It's like we learn it so much that we can tell the buyer a better way to search for what he wants. So again, this is another example, very similar, positive, negative examples, and then we come up with the result. Pay attention to the query in this case. I will come back a few slides. This is what the user wants. This is what our system produced. Not only he got what he would like to have, but we have a very compact way to do it. Do you understand that? In a minute, you are going to understand the value of this contribution. So far, semiotic machines are gathering momentum. We are working on many details. There are many possibilities to be incorporated. I will name some of them. And of course, there is a huge potential to apply this as a tool. But I'm very close to the end, so pay attention to this because I think it will summarize most of the message here. So when you have the SADA model, we would like to incorporate individualization in the process, not to try to use statistics. So it's like the user is control of himself. You are not going to access statistical data, but your own data. Well, this is very similar to preferences, but we are using this in a different way. We are also trying to make contextualization, because one decision in one context should be different from the same decision given another. So there are somehow a little bit of awareness, which is something important, because computer science at the moment means that the computers, the programs, they perform tasks, and they don't know, they don't have a clue, I mean the programs, of what they are doing. So semiotic machines, in a way, could be a step towards trying to tell the computers a little bit of what they are doing. This is a poetic interpretation here. So more appropriate decisions, because the decision would not be a statistical one, but one centered on the user. Also, we could have adaptation, I will show you in a minute, and a little bit of autonomy, because if you create these automatic methods, so the decisions could be somehow automatized. Of course, there are many ethical issues here that we are not going to discuss. So the good thing is that as we are using meta-heuristics, it is scalable, which is very important. And also, we can hybridize. So this is the full picture. And now I'm going to show you a summary of what we are comparison on conventional computer science and after what we are proposing here. So back to our equation. So when you have a traditional query, this is an example of use of semiotic machine. But semiotic machines can be used in other ways. But let's stick to queries. So basically, X would be the query itself. You see, it's like, if you would like Y, so you have to put something here so that this F will give you what you want. Do you understand that? Huh? So then, in a query, you have to type a query. Obviously, some people do not know how to do it, etc. And then you stick into here. Then you have to have something, a database manager, for example, that would, when you have the query, he will produce the car. That is traditional computer science. This is after our contribution. The idea here would be this: a semiotic machine used on one slide again. So have a look at this. Do you see something? It's inverted, isn't it? So basically, we are using semiotic machines to invert the order of things. So basically, what we are doing, look what is out here. X. So the idea is you start with your car, then you have semiotic machines, and then you end up with your query. Do you understand the difference? You may ask, well, but deep learning does this. I can stick pictures and I have the results. But let me ask you a question. What are the results of deep learning? Other photographs. Do you understand that? So deep learning in this application would produce you other pictures. Can you see the difference and the advantage of having a query, not a picture? Because you can play with that. You can play with this. You can adjust. If you are a user without experience, there is no need for you to talk about queries. Of course, it may seem to you that the bits on semiotics are not there, but they are absolutely here. Of course, we are in the beginning. There are many things to do, but this can only be done because we studied philosophy, and I encourage scientists to do that. Engineers. Engineers in general don't like philosophy, which is a problem. So, to wrap up, there are many collaborations at work. So with Münster, which is the university, my colleagues work. So we have been doing this stuff. I mean, working on some advancements. But we are starting to discuss applications on decision-aware tasks. In Texas, we've discussed about stability, dynamic systems. There is an interest then is there on semiotic chaining, because there is a philosophy professor in the School of Engineering. This is, I did not tell you that. In Exeter, for example, we could mix this with network science, because if we, for example, could gather information from the network, the level of signification would be much better. But those are collaborations. This one, I'm just presenting to my colleague right now. He does not know that. Okay, so the goals are very high: automatic feature selection, acquisition of facts, intercurrence prioritization. So imagine if we have a system that is able to identify what is going on, he's not performing a rule-based system anymore. It is taking decisions. Automatic output assessment. So lots of things. So the final thought, I would like to just, you know, when you talk about semiotics, the most famous semiotician that unfortunately has died is Umberto Eco. This is a thought of his. Semiotics is a general theory of all things, existing languages, all forms of communication, visual, tactile, and so on. There is general semiotics, which is a philosophical approach. And to this field, then, there are many other specific semiotics. Our contribution is semiotic machines, and this is what we claim, is a bridge between minds and machines. If we are going to do that completely, I don't know, but at least the first steps are done. So I would like to take an opportunity to make a comment on Professor Zade, who has passed recently. This man was really a very, very important person to mathematics, to computer science. I think history will praise him the right honor. Okay, so let me just make a small announcement. We wrote a book on artificial intelligence and learning for kids. This is the first book for kids. So if you are interested, this is for the parents to read for the kids. But this is with illustration and stuff. It's in Amazon. Thank you very much.
Any questions?
Fernando, thanks for the talk. My question is mostly regarding how close we are to actually being able to actually produce those semiotic machines, right? So yeah. I understand the concept of it and the benefits of having that explainability, right? But how easy it is to actually do one?
Well, there are many bottlenecks, many. The first one is we are not completely free from humans, and this is not my goal. I think, and this is out of discussions with Professor Principi during my stay there, I think humans should be in all systems, but piloting the system. And one of the bottlenecks related to your question is exactly, for example, to set the goals. It's not to tell the machine what a glass is about, but that we need to find devices that can help me to see better. So this cue, which can be done just once, it's difficult for the machine, which is the left-hand side of the equation. It's difficult to come up automatically. So the human has to kick the process, okay? Which is okay, because the machines will not be completely autonomous. So that is one bottleneck. Therefore, we are not close to machines that can operate by themselves. We are not close. But provided there is a good link between the machines and the humans, if the humans point out the direction, then I would say that we are not far from having machines to accomplish tasks that not only they did not know how to do, but they did not know what the meaning of that. We are not very far away from this. However, the human has to be initiating the process. I don't know how to do the beginning of that.
Any other question?
Can I ask the chair to allow my colleagues to say something? Because this work is not only mine. How about the very close PhD on Earth? Huh? In a few weeks or so?
Yeah, in 1 week from now, basically. So the idea that we had is really to use the semiotic machine to support non-technical users that want to use computational systems. And the specific case that we focus on is whenever you have a database and you want to find some items in the database, but you don't know exactly how to write queries to find the data that you want. So you know some examples about the data, but you don't know exactly how to tell the system how to get this data. And then we use a semiotic machine to exploit some preferences of the user, to understand better the semantics of what the user wants, and then we apply this, the genetic programming, self-organizing maps to first organize the data that is there in the database and find similar items regarding the one, or there are items that are similar to what the user specified to us. So in the example of the car, the user provides one car, we somehow extract some semantics of this.
That's the cue I was talking about. The user has to inform something, you see, provide the picture or the taste or...
Okay. So coming back to your question, how far are we? For the moment, we focus on more or less on SQL, the database language, and there is a simple reason for this. SQL has a very nice predecessor for this, and this is where things come together. There is an old paper by an IBM or Moshe Sloff on query by example, and we took this as one of the guidelines. That is an old approach from 1975, and in what Fernando has been describing, we combine the ideas of query by example with semiotics. Yeah? And I'm not going to say anything further, but invite you to come to Dennis Talks after lunch. And there you will see the continuation.
Good.
Thank you. We want to thank you, Professor Buarque, and also we want you to have a little
good
souvenir from Ecuador.
So look, I'm trying not to allow my computer. That was my struggle during the talk, to avoid the problem that Ronaldo had, and so I cannot move. Good. So my friend, thank you. Thank you very much. Thank you.